So for the first one, what do we do? How do we construct the range? We need to change this into an absolute allowance, right? So that would be 3,600 plus or minus a certain number of ohms. How do we figure out how many ohms that's going to be? Okay, the 20%, right? We do 3,600 times 0.2, or we can do 20 over 100 equals blank over 3,600. Either way, it's going to come out to be 720 ohms. Now then we can construct the range from that. How do we get the lower end of the range? You had the right idea. 3,600 minus 720, which is 2,880. 2, how do we get the upper end? 3,600 plus 720, 4,320. How many of you had that? How many of you had no clue where that came from? Okay. Number 2, given the range, find the ideal value and allowance. In other words, we're going back the other direction from what we just did up there. How do I find what the ideal value would be here? It's going to be right between those two numbers, right? To do that, we would add them together and divide by 2. We average them, that's 45 or 4,500 ohms. Plus or minus, I want to find that as a percent. If you didn't find the percent, if you just put in the number, that's fine for now, but we're going to find the percent. I have to find the absolute allowance first. How do I find the absolute allowance? It's just the difference between that ideal value and either one of the endpoints in my range. I can subtract either pair. So if I do 4725 minus 4,500, we get 225 ohms. That's plus or minus. But now we want that as a percent. How do we turn it into a percent? Well, a percent is out of 100. What goes on the other side of that proportion? There's somebody mumbling over there. 225 over. Go ahead, Jordan. Be brave. What goes down here? That ideal value. We cross multiply and divide, we get 5. So it's 5%. So it's 4,500 ohms plus or minus 5%. Look familiar? Let's say that we have a device that is operating at 665 watts at 70% of peak. How would I find the peak power? What do you guys think? Okay. We've got the 70%. That'll be 70 out of 100. Where's the 665 go? Yes. 665 is the 70%. The peak would be the 100%. That's what we're looking for, is that peak watts. So 100 times 665 divided by 70 is going to be 950 watts, would be peak power. RMS voltage is 71% of peak voltage. Find the peak voltage for 120 volt and for 240 volt power. What did we get? Let's do for the 120 first. What do we do? Well, 71%, 71 over 100, where's the 120 go? One hundred and 20 volt is the top. So we cross multiply and divide, we get 169. Yeah. Technically, it's 170 volts is your peak voltage on a 120 volt sine wave. It's technically 70.7%. Now for 240, here's where we can use a ratio. If RMS is 120 out of 169, 240 would be out of 338, right? Now again, we could have set up this one here and just put 240 in here instead of 120, but just want to take a little bit different approach. So find the transformer ratio if the primary side has 800 turns and the secondary side has 50 turns. What goes on top in the ratio? 50 over 800. And of course, those can be reduced by 50, giving us 1 over 16. That's the 1 to 16 ratio. So whatever the secondary voltage is, it's going to be 1/16 of the primary voltage. So if I have a bridge like this, what's my bridge ratio? Bridge ratio is R1 over R2. Might have given it away a little bit there. What goes on top? 180. Of course, the ohms are going to divide out. On bottom will be the 270. Both of those reduces to 2/3. They both divide by 90. So it's a 2 to 3 ratio. All look familiar? Okay. A couple of you are still finishing up the quiz, and that's fine. Please feel free to take as much time as you need. I want to cover a new topic for us today, and that is PPM. Not talking about the little supplementary textbook with your other one from last semester. What PPM stands for is parts per million. And it literally is out of 1 million. Of course, this kind of forms an analog with our percents, where our percents are out of 100. And we'll look at being able to convert between the two of those in a little bit. But certain regulations, you are allowed on benzene, for example. You are allowed 16 ppm in drinking water. So what that means is if you have let's say 2,000 gallons of water, how much benzene can be in that water before it's considered polluted? Well, 16 parts per million is 16 over a million. How much is that out of 2,000? We would cross multiply and divide. 16 times 2,000 divided by 1 million. Is what, 0.032? So 0.032 gallons is all that can be in there. Let's look at it this way. I actually just forgot the number now. Gasoline contains benzene. Let's find what percent benzene is in gasoline. I spelled benzene wrong, apparently. 0.62%. So 0.62%. Doesn't seem like a lot, does it? So 1 gallon of gasoline contains, how many gallons of benzene? Well, 0.62, if I do it as a rate, is 0.0062, right? Times 1 gallon, that is 0.0062 gallons of benzene. That doesn't sound like much, does it? But if we look at that 16 parts per million, we have 0.0062 gallons of benzene. If we cross multiply and divide, point 0.0062 times 1 million divided by 16, we just polluted 387.5. You got her. Gallons of drinking water. And actually, I think the EPA a couple of years ago lowered that recommendation from 16 to like 6 parts per million. Let's say a room that has, well, let's just do this. That is 16 feet by 24 feet with an 8-foot ceiling, has 2 cubic feet of propane released into it. Find parts per million and percent. Well, first thing we need to do is find the total volume of the room. How do I find the volume of the room? You got it. 16 times 24 times 8, which is 3,072. You got it. Cubic feet. We have 2 cubic feet of propane. I was going to say 15 gallons of propane because that's how it's usually measured, but I didn't. I'll save you guys that conversion from 15 to 2 cubic feet. Parts per million. Of course, that would be out of a million. That ends up being 651 parts per million. Does that look great to everybody? Percent. If I cross multiply and divide there, .0651%. Does that look right? You'll notice, by the way, the direct conversion there. It's the same digits. All that's changed is the decimal place. How far did the decimal point move? Well, it's pretty easy to to figure that out. But let's look at from here, the decimal point went from there to here, which is 4 places. Why is it 4 places? Well, let's look here. How many zeros are on 100? 2. And how many zeros are on 1,000,000? 6. So there's a difference of 4 zeros, 4 decimal places. So if I want to convert 0.0023% into parts per million, what's it going to be? How many places do I move the decimal point? 4. So it's 23 parts per million. Or the other side of that, if I have, let's say 3.8 parts per million, what percent is that going to be? Got to move it 4 spots, add those zeros in there. It's 0.0038%. Any questions? Okay, I'm going to give you a packet. In this packet, it's going to be pages 258 through 259, 1 through 16. Actually, I believe that's in the packet you already have. That'll be questions on working with parts per million. For those of you that still need to finish up the quiz, I'll let you guys have the rest of the time to get started on the homework and finish up your quiz.